In a sealed laboratory at NASA's Ames Research Center, a spectrometer registered a signal that nobody on the overnight shift could explain. The sample inside the chamber was lunar, drawn from shadowed craters near the Moon's south pole. According to internal reports that later surfaced in peer-reviewed discussion, the water locked inside that ice was not behaving like dead water. Something in it was moving. Something in it appeared to be metabolizing. For 6 decades, the story we were told about the Moon was simple. Dry, dead. A sterile rock orbiting a living planet, scoured by radiation and baked by unfiltered sunlight. But that story started cracking in 2009, when the LCROSS mission deliberately slammed an impactor into the Cabeus crater and watched a plume of debris rise into space. Inside that plume, instruments detected something that rewrote planetary science overnight. Water. Real, measurable water trapped in the permanently shadowed floors of craters that had not seen sunlight in billions of years. That discovery alone would have been historic. But the follow-up missions kept pushing deeper. By the early 2020s, the Moon Mineralogy Mapper aboard India's Chandrayaan-1 had confirmed water signatures across large portions of the lunar surface. NASA's SOFIA airborne telescope detected molecular water in sunlit regions, not just in the deep cold traps. Estimates of the total water locked inside the Moon climbed into the hundreds of millions of tons. And then, according to researchers working with returned sample data and remote spectrometry, something unusual began appearing in the chemistry of that ice. Organic molecules. Amino acid precursors. Isotope ratios that, in the words of one planetary scientist quoted in the 2023 conference paper, looked, quote, more biological than geological. This is where the story gets strange. And this is where the careful, measured language of science has started to soften just enough to let in a possibility that almost nobody wanted to take seriously. What if the Moon's water is not just a resource waiting for future astronauts? What if something is already using it? To understand why serious researchers are now entertaining this idea, you have to go back further than LCROSS, further than Apollo, all the way back to a theory that was laughed out of most university lecture halls for most of the 20th century. Panspermia, the idea that life, or the building blocks of life, travels between worlds on meteors, on comets, on the dust kicked up by impacts. For most of the 20th century, panspermia was considered fringe, a curiosity at best. But in the last 20 years, evidence has been accumulating that tough microbial life can survive conditions once thought to be absolutely lethal. Tardigrades have been exposed to the vacuum of space aboard the International Space Station and returned alive. Bacterial spores recovered from deep ice cores have been revived after being frozen for hundreds of thousands of years. Extremophiles have been found in the cores of nuclear reactors inside volcanic vents in salt crystals sealed for 250 million years. The old assumption that life requires a narrow band of temperature and pressure and chemistry has collapsed. Life, as we now understand it, is astonishingly stubborn. And the Moon, we now know, is not as sterile as we once believed. The permanently shadowed regions inside craters like Shackleton and Cabeus sit at temperatures around -240 degrees Celsius, colder than Pluto, cold enough to preserve volatile compounds, including water, for literally billions of years. If anything ever landed there, either from Earth, from Mars, from a comet passing through the inner solar system, those conditions would have acted less like a graveyard and more like a freezer. Here's where the recent anomalies come in. According to a series of papers and conference presentations from 2023 and 2024, spectral readings of certain lunar ice deposits show features that don't cleanly match predictions for pure water ice contaminated by mineral dust. Some readings suggest the presence of complex carbon chains. Others suggest isotope fractionation patterns, the subtle differences in the ratios of heavy and light atoms that on Earth are usually associated with biological processes. One research team, working with reanalyzed data from the Lunar Reconnaissance Orbiter, reportedly identified a localized thermal signature inside a polar crater that didn't match the expected geothermal background. The anomaly was small, a few hundredths of a degree warmer than surrounding ice. But it persisted across multiple observations, and it sat exactly where the strongest water signatures had been recorded. Warmth, even slight warmth, inside a crater that should be one of the coldest places in the solar system. That detail alone is small enough to miss in a summary paper. But once you have spent time with the data, it becomes genuinely difficult to unsee. Because the lunar South Pole is not supposed to have warm spots. The physics of the place is one-directional. Heat flows out, radiation does its slow damage. Time grinds everything toward the same background cold. Finding a pocket that refuses to match that background is the kind of thing that, in a different solar body, would already be triggering international interest. On the moon, because the moon is supposed to be dead, the finding has mostly stayed quiet. A footnote, a discussion item in an internal briefing. Stack these small details together, though, and the footnote starts to feel heavier than it should. Now, before this goes anywhere further, the skeptical perspective needs to sit at the center of the table, not at the edge. At the center. Because this is exactly the kind of story that excites people far beyond what the evidence actually supports. Dr. Paul Hayne, a planetary scientist who has spent years studying lunar cold traps, has publicly cautioned against the temptation to interpret every anomaly as biology. According to his work, thermal fluctuations inside shadowed craters can be caused by subtle geometries, by tiny amounts of scattered light bouncing off crater walls, by micrometeorite impacts redistributing heat in ways that models don't yet fully capture. Isotope ratios can be altered by radiation chemistry, by cosmic rays slamming into water molecules over billions of years and creating organic-looking signatures without any biology involved at all. In other words, every single piece of evidence on the table right now has a non-biological explanation. A boring explanation, a chemistry and physics explanation. And most mainstream planetary scientists, when pressed, will point out that extraordinary claims require extraordinary evidence, and the evidence so far is suggestive at best. But here is what keeps coming up in the quieter conversations at planetary science conferences. The anomalies are not going away, they are accumulating. And each new mission adds more. India's Chandrayaan-3 lander, which touched down near the South Pole in August of 2023, reportedly detected sulfur in amounts that surprised researchers, along with trace signatures that are still being analyzed. China's Change missions have returned samples that contain tiny glass beads with water trapped inside them, some of which appear to have chemistry that doesn't cleanly match a simple impact origin. And NASA's VIPER rover, designed specifically to hunt for water ice at the South Pole, was intended to drill into deposits that could finally settle some of these questions, though the mission has seen significant changes in scope and timeline. Each mission adds a small piece to a picture that is no longer as simple as it used to be. Consider what a biosphere on the moon would actually look like if one existed. It would not be macroscopic. You would not find animals. You would not even find the kind of microbial mats you see around hydrothermal vents on Earth. What you might find, according to researchers working on astrobiology models for icy bodies, is something closer to what has been proposed for the subsurface oceans of Europa or Enceladus. Isolated pockets of liquid or slush water, shielded from radiation by meters of overlying ice, kept just barely above freezing, by residual heat from deep rock, and populated by microorganisms with metabolisms so slow that a single cell might divide once in 1,000 years. At that pace, an entire ecosystem could persist for billions of years on the smallest possible trickle of energy. It would be almost invisible to our instruments. It would leave only the faintest chemical fingerprints. And those fingerprints would look, to a cautious scientist, exactly like the ambiguous anomalies we are now seeing. One researcher, speaking informally at a conference session, described the theoretical lunar microbe as something closer to a seed than an animal. A minimal genome stripped down to the bare essentials, capable of going dormant for geological timescales, capable of reactivating only when a very specific chemical window opened, and then only long enough to pass a handful of genes forward. The rest of the time, it would simply wait. Not dead, not quite alive. Suspended in a state that no Earth organism quite matches, except perhaps the most extreme of the cryptobiotic extremophiles. Imagine a life form that has been waiting in the same place for longer than mammals have existed on Earth, doing absolutely nothing and still, by strict biological definitions, counting as alive. That is the kind of entity the environment could theoretically support, not a creature. A stillness that happens to carry information forward. There is also the question of how any life could have gotten there in the first place. One possibility is that it didn't come from anywhere else, it came from us. Specifically from Earth. Billions of years ago, when the young Earth was being battered by asteroid impacts, enormous amounts of rock and debris were ejected into space. Some of that material rained back down. Some of it escaped entirely. And some of it almost certainly ended up on the moon, if microbial life already existed on Earth at that time. And the evidence now suggests it did as early as 3.8 billion years ago. Then fragments of Earth crust carrying dormant microbes could have landed on the lunar surface and been quickly buried, quickly frozen, and quickly preserved. Not colonized in the active sense, just stored. A biological time capsule sitting a few 100,000 kilometers above us. Another possibility is cometary delivery. Comets are essentially dirty snowballs, and several of them have been shown to carry complex organic molecules, including amino acids. If a comet struck a shadowed crater at just the right angle, its volatile payload could have been captured by the cold trap instead of vaporized into space. Over billions of years, that buildup would create exactly the kind of mixed, carbon-rich ice that some of the recent spectral readings seem to describe. Neither scenario requires anything exotic. No alien intervention. No panspermic supercivilizations. Just ordinary physics, ordinary chemistry, and an unusually patient universe. A third possibility deserves a mention, even if it sits further into speculation. The moon itself may once have been more active than its current quiet appearance suggests. Lunar samples returned by Change 5 in 2020 contained traces of volcanism that were, geologically speaking, much younger than expected. Around 2 billion years younger. For a body that is supposed to have been cold and dead for most of its existence, that is a surprising window. 2 billion years of extra heat means 2 billion years of extra possibility. During that window, liquid water may have existed briefly beneath the surface. Mineral chemistry may have been more complex than anticipated, and the conditions for the origin of simple life, while still improbable, were no longer out of bounds. None of this implies that life definitely formed on the moon. Only that the door, which used to be bolted shut, is now at least slightly ajar. The implications, though, would not be ordinary. On a technical level, finding even the faintest trace of life in lunar ice would transform how we design every future mission. Contamination protocols would need to be rewritten. Sample return procedures would have to be completely overhauled. The debate over whether to allow humans back onto the lunar surface, already a sensitive topic given the renewed Artemis program, would become considerably more complicated. On a scientific level, it would settle, or at least strongly reshape, one of the oldest questions in human history. Is life rare? Is it common? Is it confined to Earth, or does it sprinkle itself across any body with the right chemistry and the right patience? If life turns out to exist even on a body as unforgiving as the moon, the logical conclusion is that life probably exists almost everywhere we care to look. Mars, Europa, Titan, Enceladus, the clouds of Venus. The implications ripple outward, rewriting entire fields in the process. On a deeper level, though, a discovery like this would force a quieter, more unsettling conversation. If something has been sitting in that ice for a billion years, the moon has not been empty while we were down here inventing fire and language and flight. It has been inhabited in the smallest, slowest, most patient way imaginable, and we almost missed it. Of course, there are reasons to stay grounded. Every dramatic astrobiology claim in history has eventually been tempered, revised, or withdrawn. The famous Martian meteorite ALH8401, which in 1996 was proposed as evidence of fossilized microbial life on Mars, is now considered by most researchers to be best explained by non-biological processes. The phosphine detection in the clouds of Venus, announced with great fanfare in 2020, has been heavily disputed and may have been a signal processing artifact. The history of astrobiology is, in many ways, a history of getting excited, then getting humbled, then learning something useful anyway. The lunar ice story could easily follow that same arc. The anomalies may turn out to be radiation chemistry, or unexpected mineral interactions, or a simple calibration issue in instruments operating at the edge of their design parameters. Most of the scientists doing this work will be the first to tell you that they expect the boring explanation to win, but they are also not closing the door, not completely, because the evidence has a stubborn way of not quite fitting. There is also an ethical dimension sitting behind this story that rarely makes it into the headlines. If life does exist, even in the smallest, slowest, most marginal form, inside lunar ice, then every mining plan, every rocket propellant extraction concept, every fuel depot proposal aimed at the South Pole, suddenly becomes a question about disturbing a native biosphere. Planetary protection protocols exist for this reason. They were written with Mars and Europa in mind. But the Moon was always considered the safe case, the body we did not have to worry about. If that assumption turns out to be even partly wrong, the legal and scientific frameworks governing lunar activity will need to be rewritten. And quickly, before the next generation of commercial and governmental landers permanently alters the environment they were supposed to study. That may sound abstract. It is not. Within the next decade, dozens of landers and rovers are scheduled to touch down in exactly the regions where the most interesting chemistry has been recorded. Some of those missions will drill. Some will melt ice. Some will introduce water, exhaust gases, and trace organic compounds from their own construction materials into environments that have been sealed for billions of years. Whatever is currently there, if anything is currently there, will likely be changed or lost before we have the tools to fully document it. That is a narrow window, and it is closing. What happens next depends on the next generation of missions. VIPER Artemis, the Chinese Lunar South Pole program, and the growing fleet of commercial landers are all converging on the same handful of craters over the coming decade. Drills will go deeper, spectrometers will get sharper, samples will come home. And one way or another, the question that is currently sitting in the margins of scientific papers will be pulled into the center of the page. Either the Moon's water turns out to be what most people assumed all along, a dead resource, useful for rocket fuel and future colonies. Or it turns out to be something stranger, something that has been quietly waiting in the dark, doing almost nothing for almost forever. It is worth lingering on how unusual this moment is, historically speaking. For most of human history, the Moon has been a symbol of romance, of madness, of gods, of calendars. It has sat in the sky as a mirror for whatever story the observing civilization wanted to tell. Only in the last 60 years have we approached it as a physical place. Only in the last 15 have we realized it carries water. And only in the last few months has the question of whether that water is sterile or not started to be treated as a legitimate, fundable, publishable research program rather than a science fiction subplot. That is a remarkable acceleration. A transition almost in real time, from certainty to uncertainty and back again. The Moon we thought we knew is being replaced by a moon we are only beginning to understand. And the replacement is not complete. We are, right now, somewhere in the middle of that swap, carrying ideas from two different versions of the same world. That middle state is where discoveries happen, and it is also where mistakes happen. The challenge for everyone involved is to stay patient enough to tell the difference. If you had to guess right now, where would you put your money? On sterile chemistry, or on the possibility that life somewhere, somehow already beat us to the Moon? Worth sitting with that for a moment. Because the answer, whichever way it lands, is going to change more than just our view of one quiet, gray neighbor. It is going to change how we see ourselves, and where we fit in the neighborhood. And perhaps most quietly of all, it is going to change how we look up at that familiar white disk on any given night, knowing what might be looking back, patient as stone, waiting out the long dark for another 100 million years without even noticing we are here.